We just introduce you our institute. So this is the metro map in Tokyo. So it's very complicated, as you see. Well, our institute is here. So this green loop is the so-called we call Yamanote line, which is most of the main towns are along this line. And you can see a little green here. This is a palace. Imperial Palace. So this is the center of the Tokyo. And here, our institute, Tokyo Institute of Technology is located. And here, RIKEN is located, actually. But recently, our institute was merged with Tokyo Medical and Dental University here. So that now we are called, since last October, we are called now Institute of Science Tokyo. Okay? And so if you come to our campus in April, you can see these beautiful cherry blossoms. And well, this is the other side, Tokyo Medical and Dental University, and then this was merged like this. Okay, so in this lecture, I have 3 parts. We have 3 parts. The first one is a clustering hierarchical structure, matter, and nuclear halo. And then second part, I would like to concentrate more on Coulomb breakup experiments of neutron halo nuclei, where we discuss soft E1 excitation or halo structure and dineutron. And the last part, I like to concentrate on more multi-neutron clusters, systems followed by quasi-free scattering. I introduce you tetraneutron experiments and oxygen-28. And also, I'd like to show you our perspectives on the near future experiments. Okay. So first, I'd like to start from this question. Our existence depends on the subtle balance of nature. This we know. For instance, triple alpha reaction. Maybe you already heard about this. So this is a detour for the synthesis of element carbon-12 in the universe. Because carbon was not produced in the Big Bang, we know, because this is due to the mass number 5 and 8. Bound states of mass number 5 and 8 do not exist, right? So then in Big Bang, most of the nucleosynthesis occurs from protons, hydrogen into helium, and only a tiny amount of lithium were produced, but not more. Okay. But then I like to explain this triple alpha reaction, so you probably know, but still, to remind us, these 2 alphas, namely a helium-4, 2 helium-4 nuclei, meet with each other, then it might produce barium-8 resonance state, which is very unbound, 93 keV, just above the threshold. And the lifetime is only 10 to the minus 16 seconds, which is very short, of course, but long enough to sometimes meet with another alpha particles to produce carbon-12. But there's another catch, namely that the energy of barium-8 plus alpha and carbon-12 has 7.37 MeV, rather large energy gap between these states. So that Fred Hoyle said that since we exist, for that we need a state here. That is now called Hoyle state. So as Fred Hoyle predicted, this state was found just after his prediction. So now we know that barium-8 plus alpha goes into this Hoyle state, and with some minor probability, it goes to the ground state of carbon-12. So that's why we exist. So as I said, our existence depends on the subtle balance because of this state, for instance. Okay, by the way, if we look at the nuclear physics, we know that barium-8 is a famous 2 alpha cluster states. And this Hoyle state is famous alpha cluster states made of 3 alpha particles, as you know. Okay? And by the way, in the universe, this process is occurring in the helium burning stars, like red giants, like Betelgeuse in the Orions, at this temperature. Okay, so alpha clusters. So alpha clusters can be well understood by this Ikeda diagram, which was proposed many years ago. So this is excitation energies as a function of mass number of multiple of 4. So you see barium-8 is here, carbon-12 is here. This is ground state of carbon-12. This is excited state, Hall state, 3 alpha particles like this, like this. So we just pick up this part. So this is just nothing but this triple alpha reaction part, like this. So this alpha cluster appears just very close to the decay threshold that we know. Okay. So this is the concept of Ikeda diagram, basically. So this happens for the other heavier clusters, like oxygen-16 is carbon-12 plus alpha, which is also relevant to the synthesis of oxygen-16 in the universe. Okay. Now, I'd like to discuss also hierarchical structure of quantum matter world. Namely, we know that particles are categorized from quarks, hadrons, nuclei, atoms, and molecules. We know, right? So how does it relevant to clustering? Actually, we can consider already this composite particle like hadron is like a cluster in a sense. And this occurs, for instance, these 3 hierarchies are categorized into the systems with strong interactions, right? And hadron, we know that 3 quarks are confined by neutralizing color charges, right? So the neutralization is a kind of key to form this kind of cluster, I would say. Then if we look at the upper hierarchy, nucleus, okay, here, we notice that the interactions inside this hadron, which is mediated by gluons, are much stronger than the nuclear force between nucleons, right? So by confining these 3 quarks, we know that the interactions are kind of separated from this hierarchy to this hierarchy, okay? So, yeah, but if you look at these sectors, atoms and molecules, we see a similar thing happening. As you see here, so we know that the atom is composed of nucleus and electrons, and whose electric charge is basically 0 because of this. So this is like a neutralization, and due to this neutralization in the molecules, the interactions between atoms are much weaker than the electromagnetic force between nucleus and electrons. So this kind of things happen in any scales. So this is one important, I think, factors in this hierarchical structures. Okay. So now I'd like to discuss clustering at the boundary between these hierarchies. Okay, now just take a look at carbon-12 nucleus. Okay, so the ground state is carbon-12 nucleus, but if you excite this fully, this becomes just hadron gas made of 6 protons and 6 neutrons. But if you tune the excitation energy very close to the 3 alpha decay threshold, we see Hall state. Okay, now let's take a look at hadron sector. Let's take a look at lambda hyperon. Okay, if you excite lambda hyperon fully, then it becomes quarks. But if you tune the excitation energy very close to the nucleon plus K bar meson threshold, then you will see hadronic molecule lambda. It's called lambda 1405. Okay. And now, if you look at molecule and atom sectors, then you can see also similar phenomena called Feshbach molecule in the unitary limit. So these things are actually occurring the boundaries between these two hierarchies and at the threshold. So we can also say that this world is closed quantum systems, and this is open quantum systems. So in the boundary of these systems, we see cluster structure or correlations. And it happens in the boundary between open and closed quantum systems in any scales and in any interaction. That's a very interesting point, I think. So, okay, so closed quantum systems and open quantum systems can be schematically shown here, okay? So the closed system is like bound states, bound nuclei, while open quantum systems are like unbound states like this way. So we know that normal particles or like nuclei, stable nuclei are kind of bound and isolated systems, so it's closed quantum systems. But particles at the edge or boundary, we see, or highly excited states, we see open quantum systems. And often, in these boundary of open closed regions, we see some exotic phenomena. Okay. So we discussed this whole state already, but now instead of okay, now let's take a look at the boron 11 nucleus. Okay, 5 proton, 6 neutron systems. But instead of changing excitation energies, now I'd like to exchange the number of protons and neutrons. Okay, so if we exchange 5 protons into 5 neutrons, then we have 11 neutrons, which is in the hadron phase. But if we just exchange 2 protons into 2 neutrons, then we have lithium-11. This is a famous neutron halo nucleus, and this may have also this dineutron cluster, and which appears also very close to the threshold, lithium-9 plus 2 neutron threshold. So this is also a kind of similar features as in the Hoyle state. Okay. Okay. And this direction is actually moving to the neutron matter, actually. Okay, and these edges, like this one or this one, may be often relevant to stellar nuclear reactions. Okay, now coming to nuclear chart. Okay, so this is the nuclear chart at the bottom part. So you see this is neutron number, proton numbers. And this line, which is called neutron drip line, is nothing but the boundary between closed quantum systems and open quantum systems, as we said. And along this neutron drip line, we see interesting features like halo structures, which was already discussed by Chen-san already, I think. Barium-11, lithium-11. Well, recently, we have observed tetraneutron candidate. As Hiyama-san discussed, we still have some controversial situation, but this is a very interesting case. And okay, so this we have several neutron halo nucleus, 2 neutron halo nucleus along this line, and we have also these white ones recently found resonances beyond the neutron drip line. So these are also interesting thing. Okay. So about the neutron drip line, experimentally, it is not yet at all established, actually. The neutron drip line has been established recently up to only neon isotopes. And very recently, only 6 years ago, we have confirmed that fluorine-31 and neon-34 are the last bound isotope of fluorine and neon isotopes. Okay? But above that, how about sodium? So for sodium, we have actually observed a new isotope, sodium-39, which was a kind of unexpected because many theoreticians believe that sodium-37 is the last bound sodium isotopes, but we found this one. So still, the sodium drip line is not yet, in a sense, fixed because maybe we see another sodium isotope even beyond. So this is a kind of frontier, current frontier over this neutron drip line. Okay. So about halo nucleus, I think Chen-san already explained this. So just to remind us, so this is a case of one neutron halo nucleus. So this is the typical 1 barium 11. So this has the core surrounded by halo neutron, in this case 1 neutron. But this phenomena happens due to the small separation energies, usually less than 1 MeV, which is much smaller than the normal nucleus of 8 MeV. And basically, because of the a very weakly bound property, the density becomes large at large distance beyond this boundary of potential. Okay, so that is so this is rather simple quantum mechanics. Okay, so extended density, neutron density distribution occurs beyond the range of nuclear force when the separation is small. For instance, if the separation energy is 0, it means that density becomes infinite. Sorry, the radius, mean radius becomes infinite. And the root mean square radius has the inversely proportional to the separation energy, in the case of S-wave neutron halo, actually. And if you, for instance, calculate the radius of halo for the separation energy 1 milli-electron volt, if it exists, we find that the radius is almost like a nanometer level. So it's very exotic in a sense, but we don't know if this exists or not. And then because of the very extended density distribution, the Fermi momentum becomes very small because of low density, or uncertainty principle. Due to uncertainty principle, the momentum becomes very small. Usually the momentum inside a core or a normal nucleus, it's like 230 MeV over C, but the neutron inside a halo has only 40 MeV over C momentum. Okay? And also for the halo formation, we need a small orbital angular momentum of S wave or P wave, because that if you have a large centrifugal barrier due to the large angular momentum, then it hinders the halo formation. Okay. So this is another condition. So this means that so if we believe the normal shell configurations, maybe neutron halo appears only occasionally because of the S or P wave configuration. But on the other hand, actually we see a lot of halos along the neutron drip line. This means that the shell evolution is also relevant for the halo formation. Okay? So these nuclear stability at the limit, shell evolution or deformation, and halo structure are all relevant to each other. Okay, so maybe I can skip this because I think Chen-san already discussed this. Okay, you can just calculate this wave function or density distribution very easily by this rather simple Schrödinger equations. Maybe I can skip this. Yeah, maybe this, okay. Yeah. I can just say that if you look at the difference between S wave, P wave, D wave for the same separation energy of 0.5 MeV, S wave has very large density distribution. Maybe this is much better to look at. So this is S wave, P wave, D wave, something like this. So if you just calculate the probability of being outside of the potential, well, with a simple calculation, then you notice that for the S wave, the separation energy is close to 0. Actually, it becomes 100% halos. But for the P wave, it's like 50%. For D wave, it's like 30% or something. So the centrifugal barrier or angular momentum is very important for the formation of the halo. Okay, I think we can skip this. We know that depending on the angular momentum, the asymptotic wave function is expressed like this: the spherical Hankel function of the first kind, like this. Okay, now I move to the 2-neutron halo. Excuse me. So this is the typical classical 2-neutron halo nucleus lithium-11. The separation energy currently known is 0.37 MeV only. And this can be described by so-called Brownian ring, I think, which was also discussed by Chen-san. And Brownian ring means that if you cut one ring, the remaining two rings are actually separated. And so in the case of lithium-11, in fact, the lithium-10 is unbound. But the scattering length absolute value is rather large, like 13 to 23 femtometer. And the neutron is also very unbound with scattering length minus 18.9 femtometer or so. But with 3-body lithium-9 plus 2 neutrons, it is bound like this. So this is a Brownian ring. So the condition of these 2-neutron halos are basically similar to the 1-neutron halo nucleus, but it's like small separation energies, extended density distribution of neutrons beyond the range of nuclear force, and small Fermi momentum, and small orbital angular momentum, L equals 0 or 1. But 2-neutron halo has a property of Brownian and dineutron correlation often. A dineutron correlation means a 2-neutron correlation spatially correlated. So I just would like to remind us about the pairing correlation in nuclei. So as I said, 2 neutrons in free space has a S-wave scattering length of minus 18.9 femtometer, okay, like this. And we know that if we put this inside a normal nucleus, like stable nucleus, we know that BCS-like pairing correlation occurs, which has been known for many years, 60 years maybe. And the property is like the coherence length is very large. Actually, it's over the size of a nucleus usually. And so it's long range, and we can say weak coupling. But Migdo predicted a different kind of neutron-neutron correlations called dineutron correlation. So it appears in the surface with short range and strong coupling. So so far, not so many examples are found for dineutron correlations. I think so we can say not yet established, but for the 2-neutron halo nuclei, we have some evidence for the neutrons. So I'll show you some examples later in this lecture. So we have some analogy of this kind of neutron-neutron correlation with the atomic systems. So in the atomic systems, using Wiltord atoms, they can actually tune the interactions between particles, Fermi particles, from the weak coupling to strong coupling. And they found that in the weak limit, they have actually Cooper pairs, BCS-like pairing. But if you go to the strong limit, then they see Bose gas and Bose-Einstein condensate often occurs. And in between, they see a crossover region, like as shown here. So this can happen also in nuclei. And this was some prediction by Matsuo-san about the density dependence. So this is density, and this is the correlation length of two neutrons, Cooper pair, I would say. Xi, RMS, and D is mean distance. And if you look at this, then this region, from 10 to the minus 4 to 10% of the nuclear saturation density, then you see D is larger than Xi. So this means that the two neutrons are correlated spatially in these density regions. So some certain density regions, we see some dineutron correlations. And you see at the normal density, saturation density, actually this Xi becomes very large. So it's like long-range pair occurs there. Okay, so this calculation is for nuclear matter, actually. This calculation is done for nuclear matter, by the way. So dineutron appears in low-dense neutron matter, but should not be too low. If it's too low, actually, again, this dineutron correlation disappears. So actually, I'll show you later one example of the experiment where this paper shows a dineutron appears near the surface of lithium-9 core in lithium-11. Okay. Okay. So why this dineutron occurs? Still, we need some work, but one important fact is that the mixture of opposite parity orbitals play an important role. Okay, so in the case of lithium-11, we know that lithium-11 has two main components. So lithium-9 core coupled to p1/2 neutrons or s1/2 neutrons. Okay, so there are mixtures different parities, P wave and S wave, okay? And if you just take expectation value of this opening angles, cosine of opening angles, so this is the opening angles between two neutrons with respect to the center of the core, okay? And take the cosine theta 1, 2, then these expectation values are like this, okay? So you have this component P and to P and S, but we have a cross term which mixes P and S like this. But since these two terms are the odd function, so we don't have values here. This is just 0, and we have only the last term. So this means that if only one component, like p1/2 only, then this means that cosine theta 1, 2 becomes 0. Okay, the same is true for only S wave component, right? So if we don't have this mixture, then we don't have any correlations, and the correlation angle becomes just 90 degrees. Okay, no correlation. But if we have these two components, then we have this cross term, so that cosine theta 1, 2 expectation value have a component like non-zero. Okay, and in the case of attractive force between these two neutrons, then theta 1, 2 expectation value becomes less than 90 degrees. While if it is repulsive, it should be larger than 90 degrees. Okay, so this is very important point. So now we find that indeed in this case, lithium-11 case, we need these two components. And this is also very important because we know that lithium-11 has 8 neutrons, right? 8 neutrons, 8 means magic number usually. So if it is magic, lithium-11 should have only p1/2 neutron. But since for some mechanism, this S-wave component, S-wave level are going down so that these two states are mixed. So in a sense, shell evolution is a kind of important factor for lithium-11 to have this dineutron correlation. Okay, so the experimentally, with this experiment, actually the component of P squared is 35%, S1 half square 59%, and D about 6%. Okay, so now I just like to summarize the 3 experimental signals of halo. One, large reaction cross-sections. The second, narrow momentum distribution of halo neutrons. And the third, soft E1 excitation or enhanced electric dipole strengths at low excitation energies. And excuse me, I'd like to discuss this in the next lecture. Okay, may I have a water? Okay, maybe this was also discussed by Jen-san, but I start from the reaction cross-section. So which is to extract the matter radius of this nucleus. So the idea was very simple. Taniata-san's idea was very simple. That if you measure the interaction cross-sections, interaction cross-section means that when lithium-11 comes, the target is here, and when you measure other than lithium-11, this means that lithium-11 is reacted with the target. And once it is reacted, it is called interaction cross-sections, sigma I. Okay? And this can be extracted rather easily by this expression. And this sigma I, in the very simplest model, like black disk model, like this one, okay? So you have projectile, like lithium-11, target is here, and the beam is coming from your side to this screen, okay? And then if the impact parameter is less than this sum of these radii, then it reacts, right? Very simple. So that cross-section is expressed by this very simple formula, pi r sum of r squared. That's very simple. And from that, they could extract Ri for helium isotope, barium isotope, lithium isotope, barium isotope, and boron isotopes like this. Okay. And if you look at this, this is the okay. So this is the mass number. So you see, this is 1.2 s a to the 1/3. So this is a normal trend of the radius. But you see enhancement for lithium-11, barium-11, barium-14, and boron-17. So from this experiment, the halo physics started. And this started actually 40 years ago. This year, we celebrate actually 40 years of halo nuclei. Okay, and then, of course, in reality, we should be more careful because this kind of approximation is only for black disk. But we know that nuclei are not at all black. So we need to use theories, so density distribution, so on and so forth. And for that, actually, this is sigma I, interaction cross-section. If you add in elastic scattering, then it becomes sigma R, reaction cross-section, which can be calculated by Glauber theory, including density distribution and nuclear-nuclear cross-sections. And then you can extract the root mean square radius, so-called. And then usually, we use this Glauber theory to extract root mean square radius of these particles. Okay, and of course, only with matter radius, that means that this is a radius including neutrons and protons, right? So we need to extract only for neutrons. For that, we need to know the actually proton density distribution, right? And for that, well, for the charge distribution, we usually use electron scattering for the stable nuclei. But the electron scattering for unstable nuclei are still not possible. We have only one example, actually, that was done at RIKEN using SCRIT system, but that was rather exceptional. And still, we need to use other method. And one of them is called this isotope shift. I think this was also discussed by you, I think. So I don't go into detail, but this isotope shift is like, if you know that the chemical properties are basically the same for all the isotopes, but not if you can measure the transition of these electrons very precisely, then you know that there is some tiny difference exists. One is due to the mass, and one is due to the field. And the mass shift is due to actually the reduced mass. It has a little bit different between, for instance, lithium 7 plus electrons, lithium 8 plus electron, lithium 8 plus electron, or lithium 11 plus electrons, right? So that is this term, and the field shift is like when electrons are here, and then you have a nucleus, and the electrons, of course, are affected by the charge distribution nucleus a little bit, right? So if the charge distribution changes, then this is like this. So yes. Okay, so if you go to especially the light nucleus, actually mass shift is larger because of this reduced mass is very important for the light systems. But if you go to heavier system, then the field shift becomes more dominant. Okay. Anyway, using this, the charge radius, or for instance, this is helium isotopes. So this is the matter radius. Matter radius is here, this one, okay? Coming from this interaction cross-section or reaction cross-section measurement. And the charge radius for helium is extracted like this. For helium-6, helium-8, this is from isotope shift. And then you can extract neutron distribution, neutron RMS radius like this. Sorry, this green one, yes. So that now you know that helium-6 has excess neutrons. So this is a helio state. For helium-8 also, it has an excessive neutron distribution. But recent interpretation is for helium-8, the radius is not so large. The tail is not so large, so we call this a neutron skin more. And for lithium, the same. So lithium-11 is here, so you see this is the root mean square radius for lithium-11. Charge radius is proton density radius is here, and then neutron density root mean square radius is here, something like this. Okay, so now what time? Maybe I should look at this. Already 40 minutes. Okay, I see. Okay, I see. So maybe I should be a little bit in a hurry. Okay, so this is a momentum distribution measurement of neutron. The first one, this is lithium-11 also. Lithium-11 impinged on carbon-12 in this case. And what they measured is lithium-9 momentum distribution, okay? And the thing is that if you measure lithium-9 momentum, this means that you measure actually the momentum of the counterpart, 2 neutrons, right? And especially in this measurement, particular measurement, they measure the vertical direction, the vertical perpendicular component of the momentum. So that, if you look at the lithium-11 rest frame or even without rest frame, for the vertical direction, anyway, this momentum is equal to the momentum of this one in amplitude, okay? So that, in this case, this lithium-9 momentum distribution was like this. And also, they measured helium-8 into helium-6, and the momentum distribution was like this, okay? So, and it was rather surprising. This is because that this momentum distribution has the width of only 17 MeV over C in this expression. This expression shows the momentum width is the product of this sigma 0, and this factor, F is fragment mass, A is the projectile mass. So in this case, it starts from lithium 11, so 11 minus 9, and this is 9, and this is 11 minus 1. Okay, this is from so-called Gold-Haber model, which I'm not going into detail, but you can find it easily, the very simple formula. Okay. And usually for stable nuclei, sigma 0 should be 90 MeV. This is also based on Fermi gas model. The simple Fermi gas model, you can find this value like 90 MeV over C, but this shows that very small number. Okay. And this was interpreted like this. So the okay, so now this is the same thing. So the neutron has actually very small momentum. Okay, very small momentum, and this narrow momentum is due to the large actually spatial distribution of the neutrons based on uncertainty principle, right? Okay. Of course, also, if you just look at the wave function, if the wave function has this form, like Yukawa type wave function, like the, as I mentioned, then actually, if you look at the momentum space, this becomes like this form, okay? So, and this k is expressed like square root of 2 mu Sn. So the separation is small, then the k becomes small, and the width is smaller. Okay. So this shows that actually neutron. Okay. So the okay, after the radius is found very large, but they have to prove that that is due to the tail of the neutrons, and so actually this clearly tells us that the tails of neutrons matters for the formation of neutron halos. Okay, so this is the first experiment, but more recent experiment actually measures also in coincidence with gamma rays. For instance, this is a case of barium 11, one neutron halo case. But not only barium 10, but they measured also gamma rays from the residue, barium 10. So this is the gamma ray spectrum of barium 10. So you see several transitions. And this means that now barium 11 has a component of this neutron halo component, but also non-halo component made of higher L orbital, d5 half, coupled to the excited barium 10 core, and so on and so forth. And those components, anyway, emit gamma rays, right? Barium 10 2 plus emit gamma rays like this. So what they did is that these components are estimated from this gamma ray measurement, and then just subtracted everything, and then found only this component, the momentum distribution like this. So now they could, yeah, okay. So the current experiments actually measures usually not only the fragment, but also some excited state component, what is going on. And with that, we could extract this very pure momentum distribution for the ground state component. Okay, so with that, I think I can just now would like to show you one very interesting experiment. Sorry. So this is, I think we can call it anatomy of neutron halo. Okay. So this experiment was published here already, so you can have a look also. But in this experiment, we use proton quasar free scattering, PPN reactions, so-called. Okay. So this is even a more advanced version of this momentum distribution measurement. So what we do is explained here. Since if we use inverse kinematics like lithium-11 beam plus proton, so we used proton target anyway. So lithium-11 beam plus proton target, okay? But if we explain like this, lithium-11 beam plus proton, it's a bit difficult. So I just use normal kinematics, namely lithium-11 is at the rest frame. Okay, so this is lithium-11, lithium-9, 2 neutrons, like this. And the proton is hitting one of the neutrons here, okay? So then what happens is that neutron is knocked out like this, and proton is also scattered like this, right? Then remaining part is lithium-9 plus neutron. So this is lithium-10 in a sense. Okay, and then lithium-10 is unbound. This is bohromium, so it decays into lithium-9 and neutron like this. And in the experiment, we measure everything, kinematically complete measurement. So we measure coming protons, neutrons, protons, and lithium-9 also. Okay. So then this is very simple. Then we would like to measure actually the momentum of this one and this one. Okay, K1, and this is just momentum conservation. So K1 is equals to K1 prime here, and K prime P here, minus incoming proton momentum, right? So we can extract momentum of neutron before the collision, okay? And then this large K is a relative momentum between lithium-9 and neutron, okay? K2 prime minus Kc prime here. But we consider that this is approximated to be close to the original, this K2 momentum minus Kc. Okay, well, this shouldn't be equal because there is some final state interaction between lithium-9 and neutron. But anyway, we think this can be a good approximation. So this means that now we can measure actually the angular correlations here, okay, like this. So as I said, we measured K1 and also large K. So in the Jacobi coordinate, this in the momentum space, we actually measure the angular angles between this K1 and large K, okay? And this is actually the conjugate of coordinate space like this. So if we can measure theta NF, then we can also make an estimation of these opening angles between this first neutron and this lithium-9 to other neutron, okay? So this is a kind of trick in this experiment. Excuse me. So the experiment was done at RI beam factory, RIBF, we call, at Riken, Japan. It's, as I explained, this is just north of Tokyo, very close to Tokyo, actually. From our university, it takes about 1.5 hours. But it is actually the most advanced RI beam facility in the world still, the third generation RI beam facility since 2007. So this is, okay, so the acceleration starts from here, and then with the cascade of cyclotrons, the energy reaches, the last cyclotron is superconducting ring cyclotron. It's the world's largest cyclotron, registered in Guinness, actually. And it provides us high-intense, high-heavy ion beams up to uranium at 345 MeV per nucleon with such intensities, okay? And using these heavy ions, one can produce radioactive beams from here. Okay, in this particular experiment for lithium-11, actually we use calcium-48 beams to produce lithium-11. Ample intensity was obtained. And the measurement was done at Samurai facility here. Okay, so this is the experiment set up at Samurai facility. So we use lithium-11 beam at 246 MeV per nu, impinged on liquid hydrogen target, proton target here. And the neutron detectors are located here. And OK, so this liquid hydrogen target we call a MINOS target. So it's a rather long, I think 10 centimeter or so, long liquid hydrogen surrounded by a time projection chamber which can track the recoil proton so that we know the vertex point event by event. And the lithium-9 is bent by the dipole magnet. This is also superconducting magnet. And it has a large gap in which the neutrons are just going through this large gap into the neutron detectors called nebula. Okay, so we measured everything like this. Okay. So this was already said. So okay, momentum of neutron K1 inside lithium-11 can be directly measured, and neutron configuration can be estimated from the remaining lithium-10. Okay. Okay, simple reaction mechanism. Effective final state interaction was minimized, and transparent probe, meaning proton can enter deep inside lithium-11, and this is kinematically complete measurement. And we also collaborated with the reaction theorists, and, this is the result. Okay. Yes? Okay, so in this case, the neutrons are knocked out very suddenly. Okay, so that if this is sudden process, then the final state interaction doesn't affect this guy going out, right? The only thing is here, but since this is also unbound state, and we don't expect very strong final state interactions. Yes?
I understand that you have now relative energy between lithium-9 and whatever.
Yes.
Do you have events where you have low relative energy between two neutrons and lithium-9? I mean, the tripod, I mean, the open quantum system, but that low relative energy of the three.
Okay, in this case, we actually measure the ground state of lithium-11, so that the, okay, so we didn't measure, because this is actually ground state. Starting from ground state, we just knocked out suddenly one neutron, so that it is not excited, actually. Lithium-11 itself is not excited in a sense. So this is a different experiment.
Okay, so you don't
Yeah.
have
Yeah, we don't have three-body reactive energies in this case. Yeah. So we just investigate the ground state of lithium-11 in this case. Okay. So we are here. Yes. So this is the result. So what you can see here is this is missing momentum K. Small k is meaning the first momentum, first knocked out momentum. Excuse me, this is K, yes. And then looked at the, okay, so there are three regions of lithium-10. So this is lithium-10, very small energies, less than 0.5 MeV. And if you select 2 to 3 MeV and all data. Okay, if you just select lithium-10, this one, at very small energies, then you see rather low momentum component like this, okay? And from the momentum component, we can actually decompose into S and P component like this. And then from 2 to 3, we see mainly P here. And for all data, actually it decomposes into S, P, A, D like this, okay? And then if you just look at then the other way, we just select these regions, very small momentum, this momentum, and second small, and the third small, and very large, like this. And then look at the angular correlations between these angles, okay? And then what we found is that basically most of them are rather flat, except for this one. This is in between 0.25 to 0.35, which is this region. Okay. Only this region, we have strong correlations. And this shows 180 degrees, means that actually in momentum space, it is 180 degrees. This means that in coordinate space, it is very small. So this region has a dineutron correlation, this means. Okay? And if you look at this, actually, this region is a mixture of S and P. So this is consistent with the picture of this mixture of different parities between these one. Okay? And also, we could extract SPD component by using this decomposition. Okay, so now this is the summary of what we have observed. So this is again the missing momentum K. So this is the momentum of the first knocked out neutron. Okay, and if you look at this, and then this is correlation angles, and you see that this correlation angles is maximized at about 0.35 femmeter inverse. Okay. So this means that this region, we have dineutrons, namely more than 90 degrees. But then it becomes more flat. So we concluded that a dineutron is kind of localized in the surface region between 10 to the minus 3 to 10 to the minus 2 of the saturation density. Okay. Like this. So now I come to the summary of the lecture. The first lecture is okay. So I think I could explain the importance of clusters, which is also relevant to hierarchies of matter or semi-hierarchies we call the alpha clusters and so on and so forth. And in the neutron dripline regions, we see some interesting clusters like dineutron related to neutrons. And I showed neutron halo physics, neutron halos, 1 neutron halo nuclei, 2 neutron halo nuclei, and especially for 2 neutron halo nuclei, we are interested in these dineutron structures. And we have 3 signals of halos: large interaction cross-sections, narrow momentum distribution, and soft E1 excitation. And in the final part, I showed one very interesting experiment using PPN. So it's called quasi-free scattering of lithium-11 to visualize kind of dineutron correlation. Okay, with that, I'd like to finish my talk, and then I'd like to accept your questions.
Okay,
Yes.
thank you very much for the nice talk. Okay, so now we can have a more question from audience. Do you have any question?
Thank you. I've got 2 questions. Like the first one, that was with the momentum distribution. So I'm familiar with like the parallel momentum distribution, you know, like when the width is small, you know, that the spatial extension will be large. And that's like a halo sign. But like I think that was like slide 27. Like you showed like the perpendicular momentum distribution. And like I don't understand like what we can get. Like you showed at some point like I think that was maybe 26 or something. Yeah. You showed these formulas. So basically, with this measure, like you measure the parallel momentum of the lithium-9 core, right? So I
Yes.
don't understand like why, like even if the core is large, that's the 2 neutron valence that give the spatial extension. So I don't understand like even if the core is large, like how do you get an information about like if it's a halo or not?
You mean that even if this is large core, but anyway, what this measured is that the momentum distribution of lithium-9 is narrow.
Yeah.
Right? So this means that the counterpart, 2 neutrons, have also this distribution.
Oh, do you know that?
Because in the rest frame, the
Okay. Yeah,
this
okay,
is just
yeah,
zero,
yeah,
right?
Yeah, okay, yeah, that makes sense. Yeah, true. Okay.
And the point is that in this particular experiment, they measured actually perpendicular component.
Okay.
So they naturally they measured actually rest frame. But the current experiment actually uses more parallel momentum distribution. Then in that case, we need to actually translate it by the, we're using the Lorentz transformation to get the rest frame momentum, but the same.
Then I've got another question that was at some point, like you were speaking about lithium-11.
Right.
And you know, like the correlation between the neutrons, like the angle, like you showed this calculate
Right.
matrix element of cosine of the angle. And then you said something about like if it's like below 90 degree, like it's repulsive or attractive.
Yes.
Like what were you talking about? Like what's, I did not understand. I did not get that point. Like,
Okay,
yeah.
so this you can understand.
Yeah.
Okay, this you can understand, and then if there is no correlation, then it becomes 90 degrees.
Yeah.
Okay, and then what I said is that anyway, if cosine theta 1,2 has this component, theta 1,2 is not 90 degrees, so it's either less than 90 degrees or larger than 90 degrees. Okay, so. If it's attractive or not, of course, this depends on some theories, but this is kind of already, I think, proved by theoreticians that if it is less than 90 degrees, it is attractive.
What is attractive, like between what and what?
Between two neutrons is attractive. This, I mean,
I think like the
if it is not 90 degrees, it's attractive, no?
Okay.
It's rather natural.
Okay. And just like a vocabulary question, like what's the difference between like a quasi-free scattering and knockout? Because for me, it's like the same.
Okay, quasi-free scattering is, I would say, same. But I mean, quasi-free scattering means that we mentioned. So quasi-free scattering is like it's like elastic scattering, proton plus a neutron or proton plus proton, elastic scattering, but proton inside nucleus. It is called quasi-free scattering, okay? But we can call it knockout reaction also. Some people call it knockout, but maybe quasi-free scattering has more, I think more precise, I would say, yes.
So I have a curiosity regarding the image you showed on the radii for the helium isotopes. So regarding the charge radius of helium-6 and helium-8,
Right.
it looks like the charge radius of helium-8 is slightly lower with respect to the one of helium-6. So I was wondering, how is this interpreted as a tighter core in the case of helium-8?
Yeah. So the interpretation is actually due to the di-neutron correlation. So actually maybe, it is. So if you see that in the case of helium-6, there is a di-neutron like this. So this means that the charge radius, you have charge here, but the charge radius is calculated from the center of mass. So the center of mass is not here, but somewhere here.
Okay.
So this distance actually adds some charge radius for helium-6. But for helium-8, this is more, like this, so that the charge, center of the charge and center of mass is closer than helium-6. That's why the charge radius of helium-6 is larger than helium-8. That is our interpretation.
Okay. Thanks.
I have a follow-up on Palm's question. So, in quasi-free scattering, you basically only knock out the outer neutrons, so the halo neutrons. Is that correct?
No. Well, in this particular case, yes. In this particular case, because we measure also lithium-9. So, but in generally, you can knock out. Anything, even inside the core also.
Right, but to study halos, is it preferable to knock out the outer ones then?
Yes, for halos, we would like to see the knockout from the halo. So that's why we also measure lithium-9 residue. Right.
Okay, thanks.
Any other question? Do we have a lot of time?
Yeah, I'm curious about the experiment. So for first of all, for this momentum distribution,
which one?
Of this measuring lithium-9 momentum, right?
You mean this one?
Yeah, this one.
Ah, okay.
So this will turn out to be measuring the relative distance between the core and the dineutron.
Right, right.
So this will not tell you any information about which partial wave this neutron is at, right?
Right.
Okay.
So this is, this is from 1988.
Yeah.
Okay, this is a first experiment to show that the neutrons have some tail.
Okay.
Okay, but they didn't say anything about dineutron correlation or whatever, how neutrons are distributed. So that's why we did this. 20 years later, we did this very precise neutron measurement.
Okay, yeah, so for that one, I'm trying to understand it a little bit better. So initially, this K1 and K2 are the momentum of the neutron in itself, right?
Inside the lithium-11, yes.
Before the collision.
Before the collision. These are the momentum before the collisions.
And after that, this you knock out one neutron, and try to understand.
So this can be measured by this momentum, right?
Okay. And in this experimental setup, you mentioned this missing momentum, which is related to this, related to K1 or K1 prime?
We measured K1 prime. Okay, in the real experiment, we use inverse kinematics anyway.
Yes.
But we basically measured incoming particles. So this corresponds to momentum of proton, incoming proton, and then knocked out proton, knocked out a neutron, and also residue lithium-9, and the neutron related to, so in reality, what happens is that so just inverted, yes, here. So inverted. So this is a knocked out proton, this is a knocked out neutron, and this neutron is from lithium-10, the K2 part. So this is K1 part.
And so the proton is not banded in the magnetic field?
No, proton is, well, if you just imagine that lithium-11 is coming like this, so the neutron inside lithium-11 hits this proton target here.
Okay.
So that it is like 45 degrees, basically. So the probability is highest at 45 degrees. And then the lithium-10 is going forward, but it decays lithium-9 and neutron.
And you're measuring the momentum of both neutrons and
both neutrons. We have different neutron detectors here. Okay. Yes.
What's the reason why use different detectors for these two?
Okay, so for these neutrons, well, we know that this is going to 45 degrees or so.
Okay.
And the space is rather limited. Okay. So the time of flight length is rather short, maybe 2 or 3 meters. So that we need rather compact neutron detectors, and also the thickness should be a couple of centimeters for this. And this has rather large one, so it has 12 centimeter thickness, 1.8 meters, and we have 120 bars here. So so that's a difference, yes.
So any other question? Okay. Obvious.
I still want to understand this plot that you made with the missing momentum of lithium in the case of lithium-11.
This one?
Yes, those ones.
Yes.
So the relative energy is the energy between the neutron lithium-10. This is the relative. And the missing momentum give you what? The momentum of the second neutron?
No, this is the first neutron. So this is, okay, so if you look at this one.
It's not clear yet.
So the first neutron is this is missing momentum. This is missing momentum, okay? So this is missing momentum measured by these three particles.
So you say K1 is pretty small?
K1 is pretty small, yes.
With respect to the center of mass of
lithium-11, yes.
Okay, so we are in the situation I was thinking.
Okay.
Yeah, so can we go back?
Yes.
So now you have this huge peak for relative energy of the neutron and lithium-9 small. So this is indication of the virtual state or not? Of course, you have higher partial waves.
Okay,
well,
so this is, okay, I see. Okay, so this is not really a lithium-10. So as I said, so lithium-9. So the missing momentum, we measure this neutron, okay? And then, okay, so this is just knocked out by the proton, right? Like this. And then, okay, so after, we have another neutron here, spectator neutron. So this is like lithium-10, actually. Yeah? Yes, that is the relative energy, as I say here. So I would say, well, okay, so we have also this spectrum. Okay, this spectrum also has, I don't have it here, but this is more like a virtual state, I would say. But yeah, but this is, yeah. So we don't call it virtual state, but I mean, this is just a momentum distribution of this guy. Okay, Dalitz plot. Yes, but the Dalitz plot is like if you have a kind of three-body state, which decays. Yeah, but this is not Dalitz plot. Yeah. Yeah, I mean we cannot make a Dalitz plot in this case because we don't have such definite, I mean, defined state, excited, defined resonance state. We I see, but okay. Well, in this case, I think we cannot extract the Dalitz plot.
Yeah, because then you could get the final state interaction, not only one part that I understand that would be in lithium-10, but maybe we could see also the information on the keyboard.
I see.
Maybe it's mixed with the Q waves and so on.
I see.
This is what then we have.
Yeah, yeah, okay.
Okay.
I think I did not get it like 100%. What is like could you point out like the difference between a neutron skin and like a halo for helium-8? What is like the key difference?
So the okay, so the neutron halo is, okay, so maybe I should, let's see. Yeah, that's actually a rather good question because some people actually still call helium-8 neutron halos. So, but for me, helium-8 is not like a halo state because, okay, so the main difference is that, as I showed, it has a tail, like, so, okay, so in the case of like this, and then you have a tail, like this, right? Like this, right? So if you have a tail like this, then we may call halo, okay? But in the case of helium-8, due to I mean, the separation energy of helium-8 is like I think 2.1 MeV. Maybe Francesca, you remember? 2.1 MeV or something. 2 neutron separation energy of helium-8. Yeah. So 2.1 MeV is rather deep, first of all. And the second, this helium-8, basically a P wave. Right? So the L equals to 1, not L equals to 0. So that we think that the density distribution doesn't have such a strong tail. But on the other hand, for helium-6, S2N is 0.97 MeV, so it's half. And yes, so that's a kind of difference. So yeah, of course, so to define the halo skin, we actually need to know that this distribution more precisely. Yes. Yeah.
Okay, so is it more like that because of this difference of a factor of 2, that like this tail structure is in S-wave more like shifted to the outside, and it's just say at one point it is skin and the other point it isn't, or is it really like the shape differs? Like that the shape is different.
So the shape of the shape of the tail, how the tail is extended, that is kind of different.
But only about the like distance, or also about the structure? Like, is it going like with e to minus r, or like different? I don't know.
Yeah, quite. Actually, so as I said, still people are kind of not. I mean, some people call it a halo, actually. So there is no definite definition, I would say, unfortunately. But yes, yeah, as you said, maybe we should establish some more quantitative definition of halo or skin. Yeah, maybe we can discuss in halo 40 years.
Yeah, so this is quite also good to solve the question.
Like, but a semantic thing, I think.
Yeah.
But
So for me, for instance, if the helium-6 and so the neutron density is halo, so then in this case helium-8 is also deep band state. Then also, but so we can calculate theoretically and neutron density profile, right? And we can compare with helium-8 and helium-6. And then, so due to this physical reason, then the helium-8 neutron density is more inside than the helium-6. So therefore, in comparison with the helium-6, then helium-8 proton neutron density should be skin, not halo, like this. So therefore, we should compare with such kind of things, because we don't have such a definite definition about halo, like this.
Okay, so it's really just like the distance is like not like, I don't know, if you measure like the radius of an alpha particle, like saying it's 1.5 times the distance of an alpha particle, or like 2 times, and then you say at what point, okay, it's a skin or not, at the moment at least.
Yeah, so that is also, we don't have such kind of things. But so with the helium-6, if we calculate some alpha neutron and a distance, maybe 4.5 femtometer in the helium-6. And maybe it's in the case helium-8 is more and compact, right? So therefore, it's a kind of skin, not halo, something like that. But it's depend on people.
Okay, thank you.
yeah. By the way, helium-8 is very interesting case, I think, because usually if you go to neutron drip line, separation energy becomes smaller, right? But helium-8 is exception. Compared to helium-6, helium-8 is more bound. So I'd like to know the reason, actually. Maybe you have some reason why helium 8
Maybe
is.
P wave attraction, P wave potential attraction is so rather strong. Then maybe that is why we have some deeper bound
So
state.
maybe helium 8 is kind of closed, semi-closed.
Yeah, because 0p3 half and we have a 4 neutron and close. So therefore, the 4 neutron has a P wave attraction. So that is also the big difference. And another thing is also that we go to some D wave and S wave and rather higher partial wave. So therefore, the energy is, so the potential should be more weaker. Then sometimes it was so difficult to make a bound state. That is so, just I'm thinking about it.
I see. Okay.
Any other question?
Maybe I have
You
a
have,
comment.
okay.
Yeah.
Yeah.
I thought was very interesting, your beryllium series. And I was wondering if we start with beryllium 10 up to beryllium 14, we could say beryllium 14 is a 4-neutron halo, or not?
Yeah, that's
We are
a
discussing
yeah.
that
I
now.
think that's a good question, and yeah, yes. I would like to know actually the because okay. So the thing is that beryllium 12 itself has a S-wave component. We know, right? And beryllium 14 also. So that the how do you distinguish the S-wave neutron inside core and outside of core, right? We cannot do that. Yes, similar to carbon 22.
This is what I was wondering.
So I think this barium 14 and carbon 22, we should be a little bit careful about this three-body model, I think.
Or
Yeah,
five.
as you like. Yeah.
Okay, any other question? Okay, so if not, almost it's a time to end your lecture. So thank you very much for your talk. And half an hour break?
Yes, we can come back to 10 to 4.
Okay,
And
so
then start the discussion.
okay, so the so discussion time start
Bye.
after